ocean covers more than 70% of our planet. And NASA's PACE satellite is showing us the colors of the ocean like never before. From a single satellite, we get to learn about water, land, and air as we continue to monitor Earth's changing climate.
On February 8th, a little after 1:30 a.m. Eastern, I got to see the PACE satellite launch.
And lift off.
It lit up the sky as it made its way into space.
There goes PACE.
The PACE satellite, plankton, aerosol, cloud, ocean ecosystem.
Helping keep pace with our ever-changing ocean and atmosphere.
We're looking at tiny things, so microscopic life in the oceans, tiny particles in the atmosphere. I'm excited about PACE, not only because I love the ocean, but also because the PACE satellite will give us more information about tiny particles called aerosols, which affect climate by absorbing or reflecting sunlight. PACE is helping us spot harmful algal blooms and monitor the health of fisheries, benefiting people right here on Earth by looking down at our planet from space. Back in February, I got to travel to Florida to learn from NASA scientists about PACE just before it launched.
Bridget Seegers and Ivona Cetinić are both oceanographers affiliated with NASA Goddard Space Flight Center, and they're here with me today to talk about PACE. It's so nice to have you here.
Great to be here.
Thank you for inviting us.
So PACE is going to tell us a lot about the ocean, but it also has information about the atmosphere. And so Ivona, can you tell us what PACE will help us understand about the atmosphere?
PACE is ocean and atmospheric mission. So on one side, we're going to extend the knowledge that we have been already collecting using other NASA satellites, about clouds and aerosols. But in addition, some specific twists that we're going to be talking about later is going to allow us to see so much more into the atmospheric properties, especially how aerosols and clouds are kind of like working together to control our climate.
How do aerosols and clouds affect climate?
Yes, that's a great question. So both clouds and aerosol, interact with light. They can reflect light, they can absorb light. But one thing that is really interesting from the climate perspective is that aerosols actually initiate formation of the clouds. So when we want to know where the clouds are going, where they're coming from, how are they formed, we cannot just look at the clouds, we have to understand the aerosols that are around there. So by using the information that PACE is going to be collecting, both from our main instrument and polarimeters that we have, we're going to be able to look at different types of aerosols, different type of little cloud droplets, and how do they interact. And once we understand that interaction better, we can talk about the climate, but also just talking about day-to-day weather. That's also going to be helpful for that.
Oh, that's fascinating. Understanding these aerosols will help us better with weather and better understand and predict climate as well.
Air quality and everything, but really that interaction is really important for the climate perspective.
Well, I do want to talk a little bit about ocean. One of the things that I've found fascinating as I've been talking to people on the PACE science team is all of the different ways that PACE will help us understand what's happening in our communities and the impacts it'll have on coastal communities. So Bridget, can you tell me a little bit more about that?
Sure. Historically with our satellites, we've been really good about telling us that there are phytoplankton somewhere or algae somewhere, and if there's a lot or a little, but we've never really been able to tease out what type is growing there. And for our coastal communities like fishing, swimming, recreation, the type of algae really matters because you can end up with a situation called a harmful algal bloom where you have lots and lots of algae, which we call a bloom, and it's causing problems often because the algae themselves produce toxins. And so that's going to have all sorts of impacts on the community. You might have to stop fishing, people can't swim. Like here in Florida, there's a red tide, you can't even go to the beach and walk around. And with PACE, it's going to allow us to kind of tell those harmful algae from the non-harmful ones, and it's going to allow people to kind of monitor better and then respond to the situation.
Oh, that's fascinating. So I want to come back to talk a little bit more about phytoplankton, but first I want to move outside of the coast into the open ocean. Ivona, can you tell us a little more about how PACE will help the open ocean?
Definitely. So as Bridget said beautifully, there's phytoplankton close to the coast, but there's phytoplankton out in the open ocean. And they do kind of a little bit different service to us. What they do there, they want, support the oceanic ecosystem because they are the base of the marine food web. But on the other side, while doing so, they're helping carbon flow from the atmosphere into the ocean. So through the process of photosynthesis, which is a complicated word, they kind of like inhale carbon dioxide and convert it into the sugars. And now these sugars are feeding all the other creatures in the ocean, you know, ultimately fish that we eat and dolphins that we like and things like that. But the path that the carbon will take and how long will it stay in the ocean ultimately starts with the phytoplankton and for the type of phytoplankton. So currently now, as Bridget said, we kind of look, it's like, oh, like there's phytoplankton, it's taking carbon, we know, but where does that carbon go? We don't know. By being able to see the diversity of the phytoplankton in open ocean communities, we're going to be able to model much better where that carbon is going. Is it going to be sequestered for a very long period of time, so taken down into the depths of the ocean, or is it just going to stay in the surface and then be returned to the atmosphere? Because then ultimately that controls that exchange of the carbon dioxide with the atmosphere itself.
Yeah, and that exchange really matters for climate as well.
Exactly.
My understanding is PACE is really going to help us with understanding fisheries. Can you talk a little bit about that?
Yeah, the phytoplankton are a really important part of the fishery because they're the base of the food chain, right? So, you know, the phytoplankton grow and little things eat them, and then a slightly bigger fish, and then, you know, you end up with, you know, larger fish in our fisheries. Also, our shellfish, they filter the phytoplankton and eat it directly. With PACE, because we can tell again the toxic from the non-toxic algae, it's going to be really helpful if you have like an oyster farm and the satellite alerts you to an upcoming toxic bloom, then you might be able to like harvest those oysters a little bit earlier or respond to that information. So it's going to be really like a nice tool, another, you know, little bit of information to allow those fishers to make decisions they need to make.
Oh, perfect. And what about like open ocean and other fisheries?
Yeah, so you can use this information that you can get from PACE. So like, you can say how much carbon is in each group. And if you know that specific fish likes to eat a specific type of phytoplankton, you can actually pretty much model how much food does that fishery type of fish get. So if you're interested in your fishing yield and in predicting the fishing yield for like big fishing industries, you can take PACE data and actually model that. So we've been doing lots of collaboration with NOAA, try to work with them to get them the data from PACE so they can actually put it in their models and try to understand the changes in the fisheries. So it's pretty cool.
And you mentioned something about, you know, working with NOAA. That's a really important part of the PACE mission, right? Working with the people that will use the data.
Exactly. We have a really good applications program where we have been for the last 3 years or so training people not just in US-based agencies, but all around the world to understand what kind of data will PACE bring and how can that data help them, and train them how to use the data right away as soon as we start making them.
Bridget, could you tell me a little bit more about how different communities will benefit from PACE data and how NASA's working with those communities to use it?
So if you think about PACE very generally, you could think about it as a water quality like monitoring tool. So it's going to benefit people in all sorts of ways. So, you know, definitely like fishers and things like that, but also the water quality has a big impact on economically too. So it's going to drive things like tourism. So it's going to allow, you know, regions to plan like, hey, if we're having more toxic algal blooms, like maybe we can use the satellite data to find like a better area where we could direct people and then still get a draw into the area. So it's going to inform people like that. Also, it can be used on freshwater. So drinking water monitoring is really, really important. So it's going to give some insights into that. And water quality has impacts on other things like home prices, and you know, it just like really trickles down. So it's a very broad, you know, group of people who can use that data.
And that's something that's really important at NASA in general, is how can we benefit people and help them understand what's happening where they live. Well, you've both described very different types of phytoplankton that have different impacts. So from harmful algal blooms to transfer of carbon. I think phytoplankton are a lot more diverse than people think. So it's one word, but it's capturing a whole host of different communities. And so let's watch a video to learn more.
One phytoplankton cannot do too much, but so many of them actually control everything what we have, our food, our air that we breathe, and our climate. They're so powerful.
Tiny Titans, the phytofighters, are out to do battle on the seas. The evil Alexandrium is up to his old schemes.
My suction toxins will poison your precious shellfish. You're no match for Dinophysis.
Dinophysis steals pigments from the phytofighters, but Protoparadinium lights up the battle with its bioluminescence. Who will reign marine supreme?
Go, Emiliana!
Only the phytofighters will decide the true fate of the seas. Each sold separately.
They're just insanely important. I mean, there's many things that are important, but these are insanely important. Plankton generally doesn't really mean like a taxonomic group of things. Like, we think about mammals and then plants, and plankton are not that. Plankton are really defined by the way they live. Plankton means the wanderer in Greek, and these are just oceanic organisms that really just don't swim that fast that they can fight the ocean currents. It's a really non-traditional way of thinking about biology in a sense. Plankton we can define traditionally in zooplankton, so something that is kind of more animal-like, and phytoplankton, something that is more plant-like. All phytoplankton does process that we call photosynthesis. They take carbon dioxide and carbon in organic form, capture some of the sunlight, and then produce carbohydrates, or just simply said sugars. They now are carrying that sun energy and push it into the food system of the ocean. And while they're doing all that stuff, they also produce the oxygen. So opposite from us, we inhale oxygen, exhale carbon dioxide. So that's why they're really important. That's why we love them so much. And that's why they're like really crucial for the whole life on the earth. Phytoplankton itself, its diversity is gigantic. I think there's like 10,000 species and each of them has a specific role. Why is there so much diversity in something that is so teeny tiny? It's fantasy, science fiction, and horror comes together. I mean, it's just so beautiful. But there's certain type of phytoplankton called coccolithophores, and specifically the most famous one is Emiliania huxleyi. But they take this inorganic carbon to make that something like a shell in which they live in. Their calcium carbonate, which they make, which is pretty much chalk, they make it in a shape of these hubcaps. And if you think about how teeny tiny they are, they're like, I don't know, I can put probably like 30 or 40 or 50 of them in the width of my hair. When they bloom, once they die, not only they take that normal like sugar carbon that they produce, but they also take that calcium carbonate, that inorganic, that chalky material down to the bottom of the ocean. So they're really, really good for exporting carbon. Removing it from this contact with the atmosphere, which is really important when it comes to the flow of carbon in the whole, Earth ecosystem, but also control of the carbon in the atmosphere. So Alexandrium is a very specific type of phytoplankton. It's called a dinoflagellate. So it's kind of like maybe plant, maybe zooplankton, maybe it's animal, maybe it can be both, no? But one thing that it does, it makes this very, 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 very powerful toxin. They're causing problems in Gulf of Maine. Alexandrium, you don't have to have a lot. Actually, really low numbers of Alexandrium can be present and produce really detrimental effect on humanity that feeds on this shellfish. So the changes of the color of the ocean due to the presence of this phytoplankton are just so miniature, no? We cannot see it with our eyes, but if we have sensitive instruments such as ocean color instrument on PACE, we're going to be able to differentiate not only because it's sensitive to the intensity, but it's also sensitive to the colors. Having this hyperspectral view with really high sensitivity is going to allow me to differentiate much, much more of the phytoplankton because each of them, or at least each group, has its own optical patterns. It's an optical fingerprint. We're hoping that PACE, due to its capabilities, is going to be able to really focus on specific species of interest, such as the harmful algal bloom species or species that are very beneficial for the growth of certain organisms. So this speciation is a function of the technical abilities that PACE has, but it's a function of our capabilities to understand the local ecosystem.
Well, I'm gonna need one of those phyto fighters for my office.
You mean one of these?
Oh my goodness, you have stickers. I'm definitely gonna need one of those.
I'll get you some later.
Thank you. Well, I understand you guys have had a busy day today. You spent some time down at the water at Kennedy Space Center collecting water samples. Do you know what kinds of phytoplankton are in those samples yet?
Yeah, so we went to a dock not too far from here and we brought our trusty plankton net. So yeah, it's kind of interesting to think about how you sample for something that's microscopic. So this is a net that has very, very fine mesh, so it's finer than like a human hair width. And so what happens when we drag it through the water is that the water comes out, but the little organisms themselves get stuck in here, and then we can take that sample, concentrates it, and then we return to the lab and we can look at it under a microscope. So it's a really neat way to just like really concentrate what we're looking at. It was an adventure day, very busy indeed. There was a gator sitting just, a few feet off the dock, so we got to, think about that and deal with that. Ivona actually, had a chance to look at some of the samples, so she can tell us more about what we're seeing in them.
And I'm gonna slide it under and we're gonna see what we're gonna see, I don't know, some magic maybe, some party people.
Yeah, okay. Oh, wow, okay, very nice.
Okay, oh wow. So what you're seeing here, it's called a diatom. Yeah, so we were just collecting here close by and it was a very, very diverse community. We saw so many different types of phytoplankton. We saw the potentially bad ones. We don't know if they're bad, but they fall in a group that makes the bad ones. So they call dinoflagellates. We saw some that I really like a lot, diatoms. They're like little phytoplankton that lives in like a glass cages. They're beautiful, important for the carbon export. We saw so many of them. We saw some little zooplankton, but we also saw pollen, and that kind of brings back to the whole story that that pollen that fell into the water. We see it under a microscope, but actually came from the atmosphere. So that's one of the things that PACE is going to look at, this connection between the atmosphere and the ocean and how they interact.
Yeah, and what you saw, it would be different everywhere you go, it would be different at different points in the year, is that right?
Exactly. Like ocean ecosystems are crazily diverse. We don't think about it because, it's all blue, but you have the jungles, you have the meadows, you have the oak forest, you have everything, and it changes. There's seasons and everything.
And that's what PACE is going to help us understand.
Exactly.
The ocean and the water, they touch all of us, right? We each have our own personal relationship with the water. I grew up in Maryland. I spent a lot of time crabbing and eating shellfish, and I know some of what PACE will do will help shellfish communities, which I find fascinating and very helpful. But you guys both also have ties to the ocean. So I know, Bridget, you surf?
Yeah, that's right. I am a surfer. I grew up in Wisconsin, fell in love with water, and then moved to San Diego, where I have very easy access to the waves. And in terms of surfing and water quality, PACE is going to be great because, again, it's going to allow us to kind of keep track of maybe toxic blooms, make sure that we're keeping people away from the water when it's not safe and letting us know when the water quality is really good and we should be out exploring. And so, yeah, it's my favorite place to be for sure.
Nice. And PACE will tell you more about when you can go to surf and when you can't based on water quality. Nice. And Ivona, you also have ties to the ocean.
Oh yeah, I have many ties to the ocean, but the one that brought me to oceanography was the fact that my parents come from two different islands in Croatia, and the life on a small island depends so much on the ocean, everything, and your food, your livelihood, getting to the places where you have to go, everything is so interacted. So ocean for me is not just again, food or play, it's part of my culture and everything. And that's what brought me to be an oceanographer and ultimately work on PACE.
So I'm always interested to hear how people became scientists. So let's start with you, Bridget. What was your path to becoming a scientist?
It was a little bit windy, to be honest, but I did study biology in college, and I came out and I was a teacher in a variety of different settings. I taught in northern Minnesota, out in Boston, and then I ended up teaching at the aquarium in San Diego, Birch Aquarium. And that was great, and so I had kind of a teaching seasonal job, school year, and so I ended up volunteering then on some research cruises and getting exposed to oceanography, and then they hired me one summer as a technician, and so after that exposure and working with the scientists and learning more about it, I decided to go back to school and then train to be an oceanographer.
Different sizes, although tiny, and then also different colors, which is going to be really, really important.
And I was really motivated as well as, you look around and there's a lot of issues that we need to address on this planet, and being able to truly understand the issues and then hopefully create information that people can respond to. So I've been very interested in creating knowledge that is actionable and kind of empowering people to respond in a good way to what's happening around us.
Well, I'm less windy than you, kind of partially windy. So I did my undergrad in biology, and then I was your typical phytoplankton person, which means spends lots of time in microscope. I went to research cruise. That's where magic happens, and there was a group of people that was doing ocean optics, which is pretty much what we do right now. You look at the ocean and ocean color. And it had lots of flashing instruments, and I'm like a crow. I like things that flashy, glittery. So I was like, ooh, what's that? And oh, we look at the phytoplankton. I'm like, you don't have to microscope? And they're like, no. And at that point, I packed up my stuff, came to US, completely dropped my first PhD, went to a completely new PhD, and I've been in ocean color since, and I'm loving it. Just doing great stuff. you might have a similar story or no?
My undergraduate degrees are actually in math and computer science. So when I was finishing high school, I didn't know what I wanted to do. I just knew I liked math. But I always grew up spending a lot of time outside. So I went crabbing every summer, and then I spent a lot of time hiking and camping. And so when I got to grad school, I realized I could bring both those things together and started doing research on climate change and earth science, where I could think about the things I loved seeing and experiencing outside, but use my math and computer science skills to model them.
That's awesome, yeah. Cool.
Well, you know, a lot of people around the world have these ties to the ocean, and they have questions about PACE. And so our NASA social media team has been collecting questions from social media in advance. And so I'm going to ask some of these questions for you.
All right.
What kind of sensors will PACE have?
So PACE will carry 3 sensors. The primary big one is called Ocean Color Instrument. That's the one, imagine it to be something of a camera that's going to be able to see like around 250 different colors of the rainbow. So it's kind of hard to explain how. Like, you know, just imagine your basic camera, your cell phone camera it's pretty much seeing 3 main colors, and it kind of like mushes it up to make it feel real. This is going to have over 250. So that's going to give us the resolution for us to look at its diversity in the ocean, but also in the atmosphere. And it's going to have 2 more little instruments that were given to us by our collaborators.
You know, that actually takes us to our second question. Someone asked, why does it need to see more colors?
We have designed the instruments historically to tell us where there's chlorophyll, you know, and so it would measure in the green and blue and in the red and a little bit in between, and we could tell that pigment, right? So chlorophyll is a pigment. It allows the phytoplankton to do photosynthesis, so, you know, same as land plants. But the diversity of phytoplankton means there's not just chlorophyll, there's lots of other pigments. And so that's going to slightly change the color of the ocean depending on what's there. So depending on the phytoplankton, the pigments will also change. That means a slight change in color. And the old instruments were not sensitive to all those slight changes in color. So to tell the diversity, we really need to see these little changes in color that's going to tell us, you know, what's growing here and what's growing there.
Okay, so let me make sure I understand this correctly.
Yeah.
So what we had before could see just a few colors, and as a result of that, we could see where phytoplankton are.
Right.
But now we're going to see a whole lot more colors, so we want to tell what kind of phytoplankton.
Yep, exactly.
Excellent. That's fascinating.
Awesome. Yeah.
And so then our next question, what are you expecting PACE can help us understand about aerosols? I think that one's probably...
Yeah. So once again, you know, we're going to have that OCI and ocean color instrument and 2 polarimeters to look at the aerosols. And similar to, you know, the phytoplankton we talk about, there's so many different types of aerosols, you know, like, you know, it's not the aerosol from can, it's the aerosol that controls our, you know, air quality. It's the one that is produced by wildfires, is the one that is deposited, you know, think about like, you know, like a big windstorms coming from Sahara Desert and taking that dust into the ocean. Talk about volcanic eruption. There's so many different types of aerosols. So understanding the different size, the different type, once again, is going to feed into the climate, but, you know, from the oceanic, really selfish perspective, I'm really interested in these aerosols that are coming and maybe bringing some food to the ocean, and then we can see how different phytoplankton communities change based on the deposition of different types of aerosols.
Yeah, so as those aerosols enter the ocean, they bring nutrients.
Exactly.
Yeah, great. So last question from social media, what oceans will PACE study?
Which oceans? Oh, that's a great question. It's going to cover the full globe, which is great. We're going to get coverage every 2 days of the entire planet. Also, it's not just limited to the ocean. It can also be used in like some of the large like inland bodies of water, like Okeechobee here or the Great Lakes, so and inland seas. So it can go beyond the ocean. So all the oceans, full global, and then inland waters too.
Like the Great Lakes, things that are big enough, we'll be able to see them too and what's happening there.
Yeah, and it's great, and it's going to help us answer the same types of questions. Where are the phytoplankton? You know, if there's a problem, especially freshwater systems, there's a lot of drinking water.
Yeah.
And they can also have toxic algae issues. So this is really going to help with that type of monitoring.
Yeah, and the fact that we can see the whole globe, that's really the benefit of satellites, right?
Oh, yeah.
That we see all of it, not just one ocean, not just one ship track, but all of it. Oh, thank you. Any final thoughts?
I think launching satellites such as this one is going to really help answer this question, understand better as we're going forward, you know, how the food distribution is going to go, how the availability of the fresh water is going to be there, and ultimately what's going to happen with our climate.
I mean, there's so many questions, and, you know, humans have never had a data set like this. So the types of things we can start to understand and like questions that we don't even know to ask yet, and like the insights we're going to gain, it's incredible to be sitting like right on the edge of all this data coming in. and being able to see phytoplankton from space, like communities, like which one's where. That's incredible.
And
So,
aerosols.
Yeah, and aerosols, and yes, and clouds.
Well, I'm certainly excited. I mean, this is also going to show us how beautiful our oceans are and what's living in them and the aerosols. So thank you both so much for being here, and go Pace.
Hey, go Pace.
Go Pace.
Thank you.
Now I'm back in Washington, D.C., and I'm standing here today in the Earth Information Center, a place that NASA uses to show what our planet looks like today, how it's changed over time, and to provide data that can help improve lives in the face of disasters, environmental challenges, and our changing planet. If you're ever in Washington, D.C., please visit the NASA headquarters and see the Earth Information Center. And from home, you can access all of this information at earth.gov. So thank you, and see you next time.